Hello everyone, it's M. Sajjad, and today we're going to solve another Leetcode problem. This problem is merging k-sorted linked lists. Without further ado, let's read the problem statement and see how we could come up with a solution for it. As always, we're going to use TypeScript for writing the solution, but feel free to apply the algorithm to any programming language of your choice. Okay, so you are given an array of k linked lists. Each linked list is sorted in ascending order. Merging all the linked lists into one sorted linked list and return it. Lists would be 3 different linked lists which are all sorted, and the result would be this. So as an explanation, 1 links to 4, 4 links to 5. In the next linked list, 1 links to 3, 3 links to 4, and in the last linked list, 2 links to 6. Now, after merging, we have a single linked list, 1 links to 1, 2, 3, 4, 4, 5, and 6. If there is no linked lists, well, the result would be an empty linked list. And if there's a linked list which is empty, again, the result would be an empty linked list. The number of linked lists is k, which would be 10 to the power of 4, and each linked list would have 500 items maximum. Each item would be a number between minus 10 to the power of 4, which would be 10,000, to positive 10,000. And the lists is sorted in ascending order. The sum of the links will not exceed 10 to the power of 4. Okay, so let's jump to a solution. Okay, so the solution to this problem is you could iterate through all the lists, and we know all the linked lists in the lists are sorted. So the beginning of each linked list is the smallest item. We have to compare these items with each other, take the minimum one, and add it to the result linked list. And continue doing this until there is no more items in any of the linked lists, and the result linked list has the entire numbers that were previously inside the linked lists. Iterating all the linked lists for each item insertion isn't that much efficient. We could use a data structure which it's aware of the minimum element. It's called a heap, a MinHeap. So the MinHeap is a tree type of data structure which stores the minimum element at the root node. And if you're not familiar with MinHeaps or max heaps, I would add a link here so you could get more familiar with them. Just a brief explanation of what the heap does is that you have 2 operations in the heap, the insert and the remove. You insert items one by one, and the heap data structure is responsible for keeping the heap balance. It's a binary heap and it's a complete tree, so it would store the items from left to right in each level, from top to down. So if we are missing items, we are eventually missing it in the lowest level at the right side. And each parent is in the MinHeap smaller than the children. And going down the tree, it all applies in all of it. So if we insert a new item, it will readjust the tree somehow to make sure that the configuration that I just described still applies. And in the remove index, we could easily take the first element of the heap, that's the minimum, and the remove would just reconfigure the tree again to make sure that the configuration still applies without the top node. So the second smallest would be the new minimum. Unfortunately, TypeScript and JavaScript, I didn't find a library that uses heap underneath, so I have to implement it myself, and I will in this video. But the approach that we're going to take is that we're going to use an array to store the heap. In this array, each parent's children is either the left children, because it's a binary tree. The left child is stored in, if the index is I, it's 2 times I, and for the right child, it's going to be 2 times I plus 1. We have two functions, insert and remove elements. And we know that the first element of the array is always the minimum. First, we will implement the final function, which is merge lists, as you can see here. Then we would go through and implement those missing functions. So just to make sure that what we are doing is clear, we said that the heap is an array of list node or null, and the first item, the index 0, is a dummy value because we want the formula to apply, the left child and the right child being for the index I times 2 and I times 2 plus 1. So we put a dummy child in it. Okay, so now we're going to iterate through the lists. And if the lists I is not empty, because it could be an empty linked list in the lists, we would insert it. This is a magic function. We're going to use it for now, but we're going to implement it later. The lists I inside our heap. Okay, and we are doing this, as you can see, for the entire first elements of the linked lists. This we could call the initialization step. Now, if the heap.length is 1, because we put one element in it, it means there was no new elements added, and we could safely say that the linked lists were all empty. So the resulting linked list, as we saw in the problem statement, if the linked lists are all empty, we should return an empty linked list. So a null would be a good definition of an empty linked list. Okay. Now we are sure that at least one of the linked lists had a value. So the current is a list node or null would be a list node. The constructor, let's put the new keyword here as well. We are going to take the minimum element of the linked list, which would be the first element of the heap, which is heap1.val. And the results linked list would first initially, we don't know which item is next, so the next would be null. But the minimum element of the MinHeap did have a next. So the heap next, to say, would be a heap1.next. Remember, the array that we are using as a heap, each element of it is still a list node. So it still has a reference to the next element of the original list. Why are we doing this? Because we don't want to keep track of each time we remove an item from the heap as being the minimum element. We don't want to double check, okay, where was the origin of it, so that we could add the next item from that list into the heap. So next heap, the first item references the original list next, and now that we have that value, let's just put some dummy lines here. Remove minimum. This is another function, a magic function that removes the minimum from the heap, and we would implement it in the future. So if we have both those functions, then the result list would be a list node or null, which originally would be the current. Now we do a while loop. A while loop until there is no more elements in our heap. Or imagine there's only one linked list. So the lists here contains only one linked list. If we insert it here in our heap and we remove it, then obviously our heap is empty. So checking if the heap is not empty isn't sufficient. We have to also check that the next heap that we have right now is also empty. Heap next. If both of them are not empty, or one of them at least is not empty, we will continue the iterations, add items to heap, remove them, and follow our procedure. So if remember we have at line 28, we have removed an element from the heap, so we have to insert it. So if the heap next actually is containing a value, we would insert a heap next to the heap. And I think we could omit this check and make sure it's truthy. Yeah, like this. Okay, so now that we have this, the current dot next, the current is the pointer to the result linked list. It's the last item of it. So that next would be, remember, inserts function is a magic function that would adjust the heap, and we are sure that the heap 1 right now is the new minimum. So it would be a new list node, which the heap 1.val and null would be the values to it. Then the heap next again would be, because we just removed another value into the resulting linked list, so it would be heap 1.next. We remove an item, remove minimum from the heap, and the current would move one step further. At the end, we would be able to return the result list, and this result list is the linked list containing all the minimum elements. I think this part of the functions is done, so we could easily go to implementing the missing functions. Okay. One thing that we are going to use over and over again is referencing the parent node, the left child node, the right child node, swapping. These functions could be extracted to helper functions. So exactly the 4 functions that I mentioned, let's implement them. So function get parent index. So imagine we have a current index, which would be a number. We want the index of the parent. If we're going to create a heap using a binary tree, which is stored in an array, then the math.floor of current index divided by 2 is going to be the index of the parent. So function get left child index, if a parent index is passed to this, then the left child is always the parent index times 2, and get right child index for the parent index would always again be the parent index times 2 plus 1. So these are the index findings of our heap, which we use over and over again, but for simplicity reasons, we are just currently creating them to functions to make the code more readable. Then the swap index values, maybe this first index. So if we have two different indexes of the heap, which is an array of list node and null, we would swap them and return nothing. So the swap would be the decomposition, I think, in ES6, which would be heap first index, comma, heap second index being equal to heap second index and heap first index. Okay. Now we're going to implement the first easier function, which is the insert. In the insert function, there's a list node which is passed, and there's a heap which is an array of lists node or null. And the result of the insert is always a void function. It's always a void. So first, this is how we do it for the insert. We put the inserted elements at the end. We check it with the parents. With the parent, it's going to have a single parent. If it's smaller than the parent because it's a MinHeap, we're going to swap it with the parent. Then we will check it with the new parent. Again, if it's smaller than the parent, another swap. Doing this until we reach at the top of the root of the tree, or we reach to a point that it's no longer smaller than the parent. So the MinHeap doesn't need a new reconfiguration. So first, we push the X into our heap. Now, we said if the heap dot length, so it's a while first, let's just put the current index in the what's the index of the item that we have just inserted there? It's the heap dot length minus 1. And while the current index is greater than 1, because we remember the null that we put in line 37, you can see here on to the array, and it's a dummy value. So when we reach 1, it's the absolute parent, it's the root of the tree, and we don't need to go further than that. Or it's an and actually, heap dot get parent index. So this is a node list, so we have to compare the values with the val. Is smaller than, is greater, it's a MinHeap, is greater than heap current index dot val. If this is it, the swapping is necessary. Takes values of parent index and current index in the heap, and the current index is the parent index. There is no such thing as get. So it's a current index. So this again would be get parent index of the current index. Now this would be the new current index, and we're going levels up. Now this is the insert of the heap, and that's the easy part. Let's do the removal, which is going to be a little more code than the insert. Remove minimum from the heap, which is an array of least node or null, and it would return void. It's removing. So we first put the last element of the array to the head of the array, and we start checking it with the left and right child. If it's if it's greater than one of those, we slide it down. We slide it down until it goes to the right place. First, we put the first index, which is the root, as the heap of the heap dot length -1, as I mentioned, and then we pop the last element from the array. So let parent index be a number. It's a number, and the beginning is 1, right? Because the absolute parent index would be 1. So let the left child index be, it's a number, and it's get left child index of the parent index. Let the right child index be the get right child index of the parent index, and let left value could be heap left child index, but it's not always that, because left child index sometimes goes out of the scope of the array, and doing these multiple checks to make sure it's not out of scope and blah blah, it just takes too long to code it. But we don't want to repeat the code over and over again, so we just store it in a left value. I think this is more convenient like this. So it's least node or null, and it's going to be the left child index if this is greater than the heap dot length. We know we are out of bounds, so we put a null in it. Otherwise, we do a heap dot left child index. And for the right value, right child index, we're doing the same. Now we're going to do a do while, because at least we're going to do these operations once. But while there is a left child, the left value, there is a left value, and the heap parent index is greater than the left value dot val. Okay, the left parent was also a dot val. So either it's greater than the left child, or there is the right value and the heap dot parent index.val is greater than the right value.val. If one of those cases occur, then we continue doing it. We still need to glide down. We still need to continue readjusting the configuration of the tree. Okay. There are three kinds of cases. Either both the left and right value exist, or only the left value exists, because we couldn't have the right value without the left value because it's a complete tree, or none of them exist. So let's do if-else statements for these three cases. So if there is no left value left and there is no right value left, the heap was passed as reference to us. So every changes and any modification that we do with it here does affect the outside of the function as well. And if we just return, we know whatever we did is okay and is applied, and we don't have to just return anything else. But there might be a case where the right is not present. From the other hand, we have a left value because it didn't go to the top check. So we could just say if the right is there and the heap.parentIndex.value is greater than the left value.value, and we are sure that we have a left value because we didn't go to line 50 inside. Okay, in that case, we swap the index values of left child index and the parent index in the heap. Now, the parent index of ours is actually the left child index. We went one layer down. Or we are sure that right now we have both left value and right value. We could have not written those, we could infer this happened, and if this is the case, then we have to check. So if the left value dot value, remember we have two childs. These two childs are definitely greater or equal to the parent. But what is their relationship compared to each other? We have to choose the smaller one to push the parent down. And if these two are the same, we always choose the left one. So if the left value is smaller than the right value dot val, then we check it with the parent index. That makes it sufficient. You don't have to check it with the other one as well. Is greater than the left value dot val. If it's this, then we swap index values of the left child again and the parent index in the heap. And our heap, our parent index would be again the left child index. But if the right value is smaller than the left value.val, and it's really risky to write this amount of code without running it even once. Parent index.val, write value.val, then the swap index values, write value index and the parent index with the heap. Okay, we could do an else if as well. So we're sure that we're not doing this. The left child index is get left child index of the parent index. We changed the parent index a lot. Oh, see here, we forgot to do it. So the parent index is the right child index. Right child index is get right child index of the parent index, and the left value is the left child index being greater than the heap dot length. If that is the case, we call it null. Otherwise, it's heap child left child index. And for the right value, it's right child index, checking if it's greater than the heap length. Then we push a null to it. Otherwise, it's heap right child index. It might be a miracle, but it might just run. So let's just check it and press the run code for the first time to see what answer we would get. Okay. Right child index, yep. Let's see what else. Property length does not exist. Yep, a typo. Let's run the code again. And let's submit it. And accept. As you can see, I'm actually really satisfied with it. Hope you enjoyed this problem solving. Sorry it was a little longer than my previous videos, but the reason was that we had to implement the heap ourselves. If you enjoyed the video, I would appreciate if you press the thumbs up button and support my channel and subscribe to it. And if you're into Leetcoding problem solving, select either of the problems displayed here and see the solutions to it as well. Hope you enjoyed my videos. Catch you in the next one. Bye.